Find somewhere comfortable. You don't need to sit up for this, or keep your eyes open, or hold on to any of it. If words arrive and drift past without leaving a trace, that's exactly right. We're not going anywhere in a hurry tonight. If today was heavy, if it asks more of you than you had to give, you can set it down now, just here, at the edge of this. The day doesn't need anything more from you. Tonight, we're going to follow something very old and very quiet. We're going to follow sand. Ordinary sand, the kind that gets into your shoes and sits at the bottom of rivers, the kind that has been lying on the surface of this planet for hundreds of millions of years. We're going to follow it all the way to glass, to the window beside you, to the screen in your pocket, to the tiny thread of light that carries a message under the ocean floor. It's a longer journey than it sounds, and it begins not in any factory or workshop, but in the dark interior of a volcano, in the cold silence of space, in the brief and blinding moment when lightning meets desert sand. You don't need to remember any of this. Just let the words arrive slowly, the way warmth does. Long before any human hand reached into a fire and drew something out of it, the earth was already making glass. It was doing it quietly in the ways the earth does most things, through enormous patience or through sudden and total violence. There was no middle ground. Either glass formed over geological ages, deep in the slow pressure of the planet's interior, or it formed in an instant in temperatures so extreme that rock itself forgot what it was. The most ancient of these natural glasses is obsidian. You may have seen it. That dark, almost mirror-smooth volcanic stone, black as a calm night, with edges so sharp they can still be used as a cutting tool today. Surgeons have used obsidian blades in experimental procedures because under a microscope the edge is smoother than surgical steel. It is not a crystal. It is not quite a rock in the ordinary sense. It is glass, pure, ancient, volcanic glass. Here is what happens when obsidian forms. Deep beneath a volcano, magma, molten rock, builds up over years, sometimes centuries. When it finally forces its way to the surface, the silica-rich portion of that magma, which is to say the part with the highest concentration of silicon dioxide, the same compound found in ordinary sand, sometimes erupts and cools so quickly that its atoms simply cannot arrange themselves into any ordered structure. In ordinary rock, given time, atoms settle into crystals, neat, repeating patterns, like tiles on a floor. But when the cooling happens fast enough, the atoms freeze in whatever disordered arrangement they happen to be in. A liquid, in a sense, that never had time to become anything else. This is the first and most important thing to understand about glass, and we'll return to it throughout the night. Glass is not a crystal. Its atoms are frozen mid-tumble, caught between one arrangement and another, never having settled. There is something almost restful in that image. A material that simply stopped mid-motion and stayed. Stone Age peoples found obsidian and understood immediately that it was different. They couldn't have known the atomic reason why, but they knew what their hands told them. Obsidian napped, broke in controlled, predictable ways, better than almost any other stone. You could strike it at an angle and produce a blade with a curved razor edge. You could work it into an arrowhead with a precision that flint sometimes refused to offer. Obsidian tools have been found at archaeological sites across the world, in the Americas, in Africa, across Europe and the Middle East. And because obsidian from different volcanoes has a subtly different chemical composition, scientists can trace exactly which mountain a particular tool came from. There are obsidian arrowheads found in places hundreds of miles from the nearest volcanic source, which tells us that these materials were traded, carried, valued. People walked long distances to obtain this dark, silent glass. There are other natural glasses too, each with its own quiet origin story. Tektites are small, glassy objects, sometimes round, sometimes teardrop-shaped, occasionally twisted into strange aerodynamic forms that are found scattered across certain regions of the Earth in what geologists call strewn fields. The leading explanation is that they form when a large meteorite strikes the Earth with enough force to vaporize rock instantly. The vaporized material is flung upward into the atmosphere, cools rapidly as it falls back through the air, and lands as glass. Some tektites have been found to contain tiny bubbles of gas that form during their brief, violent flight. Others show flow lines frozen into their surface, evidence of the spinning and tumbling they did as they cooled through the upper air. They are, in a sense, glass tears, shed by the Earth at the moment of impact. Then there are the stranger, quieter ones. Libyan desert glass is a pale yellow-green material found across a stretch of the Sahara in western Egypt, and for decades its origin was debated. It has been dated to around 26 million years ago. The current understanding is that it formed from a meteorite impact or an airburst, an explosion in the atmosphere above the desert which melted the sand below into a vast, shallow pool of glass. Tutankhamun's tomb contained a carved scarab made from Libyan desert glass, which means that someone, thousands of years ago, found this strange pale material lying in the desert and recognized it as something worth keeping, worth shaping, worth placing in a pharaoh's burial chamber. And then there is fulgurite, perhaps the most intimate of all natural glasses, because it is made not by a volcano or a meteorite, but by a single bolt of lightning. When lightning strikes sand, the temperature at the point of contact can reach something in the region of 30,000 degrees Celsius, roughly 5 times hotter than the surface of the sun. For a fraction of a second, the sand around the strike is vaporized, melted, and fused. What remains, when the light is gone and the sound has faded across the desert, is a thin, hollow, branching tube of glass buried in the sand, a fulgurite. The shape of a lightning bolt, preserved in glass, sometimes only a few centimeters long, sometimes stretching more than a meter into the ground. They are extraordinarily fragile. They crumble if you hold them too tightly, but they are real, and they are glass, and they were made in less than a second by one of the most powerful forces in nature. There is something worth sitting with in all of this. Glass did not wait for us. It was not invented so much as discovered first by the planet itself through eruption and impact and the sudden violence of a storm. The silica that makes glass is one of the most abundant compounds on the surface of the Earth. It is everywhere. It is the sand on every beach, the dust on every plateau. All it needs is heat, enough heat, applied quickly enough, and it becomes something else entirely. Something transparent, something that holds light differently than anything around it. The people who found obsidian and shaped it into blades were not glassmakers, but they were the first humans to hold glass in their hands and understand, in whatever wordless way understanding works, that this material had something the world around them did not. It held an edge. It caught the light. It was smooth in a world that was mostly rough. The Earth had been making it for millions of years before they arrived. They simply noticed. The step from noticing glass to making it took a very long time. For thousands of years, humans worked with natural glass, obsidian, tektites, the occasional fulgurite, without ever producing it themselves. Then, somewhere around 5,500 years ago, in the river valleys of Mesopotamia and along the banks of the Nile, something changed. Exactly what changed, and exactly how, is one of the quieter mysteries of the ancient world. The most widely accepted theory is that human-made glass was not invented deliberately. It arrived as an accident, a byproduct of something else entirely. The most likely candidate is metalworking. Copper smelting had been practiced in the region for centuries before the first glass appears in the archaeological record. Smelting involves heating ore, rock containing copper, to temperatures high enough to separate the metal out. The remaining material, the waste left behind, is called slag. And some of that slag, when the ore happened to contain the right proportions of silica and other minerals, cooled into a glassy crust. Someone, at some point, looked at that crust and saw something other than waste. A second candidate is faience, a glazed material made from crushed quartz or sand, coated with a glass-like surface and fired in a kiln. Faience was being made in Egypt by around 3500 BCE, and it requires many of the same ingredients and temperatures as glass itself. It is not difficult to imagine a faience workshop where a batch was heated a little too long or a little too hot, and the whole thing melted together into something new, an accident, an interruption, a discovery. What is certain is that by around 3500 BCE, the evidence for glass appears. Small beads, fragments of glassy glaze, objects that are neither faience nor natural stone, but something in between. These early pieces were not transparent. They were colored, often deep blue or turquoise, colored by the copper compounds that were already present in the workshops where they were born. They were precious. They were worn as jewelry. They were placed in tombs. For roughly 2,000 years after its first appearance, glass remained a material of extreme luxury. It was produced in small quantities, shaped by hand or by pressing into molds, and owned only by the wealthy. Then, around 1500 BCE, something significant happened. Craftspeople in Mesopotamia and Egypt developed a technique called core forming, and with it came the first hollow glass vessels. Core forming is slow, patient work. You begin by shaping a core, a form made from a mixture of clay and dung, sometimes sand, built up around a metal rod into the rough shape of the vessel you want to make. Then you heat glass until it is soft, and you wind it around the core in threads, building up the walls of the vessel layer by layer. You smooth the surface by rolling it on a flat stone. You add handles and a rim. Then you wait for it to cool, and very carefully, you scrape out the core from the inside. The results were small: perfume bottles, containers for cosmetics, unguentaria for precious oils, that they were extraordinary. They were striped with color, wound with threads of white and yellow and blue, combed into feathered patterns. They were made to hold things that were valuable, and they were themselves valuable. We know they were traded across the ancient Mediterranean. We know they were given as diplomatic gifts. A glass vessel from this period, if you found one, would feel in your hand like something that understood its own worth. And then, in the 7th century BCE, in the library of the Assyrian king Ashurbanipal at Nineveh, a library of tens of thousands of clay tablets covering medicine, astronomy, literature, and law, there were found the oldest known written instructions for making glass. Recipes. Actual recipes pressed into clay in the cuneiform script of ancient Mesopotamia, listing ingredients and proportions and procedures. It is worth pausing on what that means. Someone around 650 BCE understood the process well enough to write it down, not just to practice it or to pass it on by demonstration, but to record it in language in the expectation that someone else might read those words and follow them. The recipe calls for specific types of sand from specific locations, because not all sand makes good glass, a fact that remains true today. It calls for particular plant ashes to be added, because those ashes contain the sodium and potassium compounds that lower the melting point of the silica. It describes the color of the fire, the appearance of the melt, the signs that things are going well or poorly. This is knowledge, organized, transmittable, hard-won knowledge about what happens when you heat sand to a very high temperature in the presence of the right additives. It took humans roughly 3,000 years of working with glass to reach the point of being able to write that down. And the basic chemistry described in those clay tablets is not fundamentally different from what happens in a glass factory today. There is something deeply human in that continuity. The recipe survived. It survived because someone understood that what they knew was worth preserving, that the knowledge of how to coax something transparent from something opaque was not obvious, not inevitable, and might be lost if it were not written down. The craftspeople who worked those ancient furnaces did so by firelight, in workshops that were probably hot and smoky and loud with the sounds of bellows and stone tools. They worked with materials they had learned to read by eye and by feel. The color of the melt telling them the temperature, the viscosity of the glass telling them when it was ready to work. They understood something that took modern science centuries to explain in formal terms. And what they made in those workshops along the Tigris and the Nile was the beginning of a tradition that has never stopped. The furnaces grew, the techniques multiplied, the knowledge spread westward, along trade routes and through the movement of skilled workers, toward the coasts of the Mediterranean. And there, on a narrow strip of land between the mountains and the sea, something was about to change everything. Imagine holding an iron pipe roughly a meter long. One end is in your hands, the other end is in a furnace, gathering a small molten ball of glass, what glassworkers call a gather, which glows somewhere between deep amber and pale gold depending on how hot it is. The gather trails slightly as it leaves the heat, already beginning to stiffen. You raise the pipe to your lips, and you breathe. That single action, a breath of air through a hollow iron pipe into a small molten ball of glass, is one of the most consequential discoveries in the history of materials. The people credited with it are Phoenician artisans, skilled craftspeople who had been working with glass for generations. Exactly who first thought to blow air into a gather of molten glass, and exactly what they were trying to do, is not recorded. What the breath does is remarkable. Molten glass at working temperature, somewhere around 1,000 degrees Celsius, behaves like very thick honey. It flows, but slowly. It stretches without breaking. It holds a shape when it cools and loses that shape again when it reheats. When you introduce a bubble of air into the center of a gather, the glass walls around that bubble are thinner than the surrounding material, and they respond to the pressure of your breath by expanding outward. The bubble grows. If you keep blowing steadily, rotating the pipe to keep the gather centered by gravity, the gather expands into a sphere, then an oval, then whatever form your hands and breath and tools guide it toward. The physics of why this works so elegantly has to do with a property called viscosity. Essentially, the resistance a fluid has to flowing. At the right temperature, molten glass has a viscosity that is extraordinarily cooperative. It is fluid enough to be shaped, but viscous enough to hold the shape you give it without collapsing under its own weight. As it cools, its viscosity increases rapidly. The glass stiffens, holds its form, stops responding to the breath. A skilled glass blower works in the narrow window between too soft and too stiff, reheating the piece in the furnace mouth when it becomes too rigid, pulling it back out to continue shaping. It is a conversation between the glass blower and the material, conducted entirely through heat and breath and the slow rotation of the pipe. Before glass blowing, making a hollow glass vessel took hours of painstaking core-forming work and produced something small and thick-walled. After glass blowing, a skilled worker could produce a vessel in minutes. The walls could be made thin, almost impossibly thin, in the hands of a master. Forms that were previously impossible became straightforward. The time and cost of production fell dramatically. The technique spread. It moved with trade and with the movement of craftspeople westward along the Mediterranean coast and into the growing territories of the Roman Empire. Roman glassworkers adopted it with enormous enthusiasm. They refined it, combined it with mold blowing, in which the inflated glass is blown into a carved mold to produce a precise shape, and developed entirely new forms. By the 1st century CE, glass had moved from the workshops of kings into ordinary Roman households. Bottles, cups, storage jars, window panes, glass was everywhere. Historians of Roman material culture have described it as the Roman plastic, and the comparison is apt. It was cheap enough to be common, versatile enough to be used for almost anything, and transparent enough to show what was inside. That transparency was itself a new achievement. Early glass was colored by the impurities in its raw materials, particularly iron compounds in the sand, which gave it a green or brown tint. Roman glassworkers discovered that adding a small amount of manganese dioxide to the batch, the mixture of raw materials fed into the furnace neutralized the color. Manganese dioxide works by oxidizing the iron compounds, changing them into a form that absorbs less visible light. The result, for the first time in history, was glass that was genuinely clear, glass through which you could see without distortion of color, glass that let the world through unchanged. Alexandria, in Egypt, became one of the great centers of Roman glass production. The city was already a place where knowledge and craft from across the ancient world converged. Its famous library, its merchant quarter, its workshops producing luxury goods for the empire. The glassworkers of Alexandria became known for the quality and variety of their output. They produced cage cups, vessels where an outer glass cage was cut back to leave it connected to the inner cup only by tiny bridges, a feat of cutting and grinding that seems almost impossible even today. They produced millefiori glass, in which bundles of colored glass rods were fused together and sliced to reveal intricate floral patterns in cross-section. They produced glass that imitated precious stones, deep purple, rich green, blood red, for people who could not afford the stones themselves. All of it rested on the breath, on the discovery that air introduced into molten glass through a simple hollow pipe could do in seconds what no other technique could do in hours. It is one of those rare moments in history where a single insight unlocks an entire world of possibility, and the person who first had it is unknown to us. Their name was not written down. What survives instead is the glass itself, in museums, in archaeological sites, in the collections of people who have spent their lives gathering fragments of ancient light. The breath that changed everything left no record except the things it made. Now we arrive at the question underneath all the others, not how glass is shaped, or who shaped it, or when, but what it actually is. What is happening inside a piece of glass at the level of atoms and bonds, and why does that make it so different from everything around it? Glass is described by scientists as an amorphous solid. Amorphous means without form, without the internal crystalline structure that most solids have. To understand why this matters, it helps to think about what a crystal actually is. In a crystal, in salt, in diamond, in the quartz you find in a river pebble, the atoms are arranged in a pattern that repeats perfectly in every direction. Each atom sits in a precise relationship to its neighbors, like a vast, three-dimensional grid extending through the entire material. This long-range order, as it is called, is what gives crystals their characteristic shapes when they grow, the flat faces and sharp angles of a quartz crystal, the cubic cleavage of salt, the perfect octahedra of diamond. Glass has none of this. In glass, the atoms are connected to each other, bonded to each other, but without any repeating pattern. If you could zoom in to the atomic scale of a piece of glass and look around, you would see a continuous network of bonds extending in every direction. But no two regions of that network would look quite the same. It is the difference between a woven fabric and a tangle of string. Both involve the same kind of connections, but one has order and one does not. The atoms doing most of the work in ordinary glass are silicon and oxygen. Each silicon atom bonds to 4 oxygen atoms, and the geometry of this bonding is very specific. The 4 oxygen atoms sit at the corners of a 4-sided pyramid shape, with the silicon at the center. This 4-cornered pyramid is called a tetrahedron, and it is the fundamental building block of both crystalline quartz and glass. In quartz, the tetrahedra stack in a perfectly repeating arrangement, sharing oxygen atoms at their corners in a precise, orderly way. In glass, the tetrahedra are still connected at their corners, still sharing oxygen atoms, but the angles at which they connect are random. One tetrahedron might connect to its neighbor at a slightly wider angle than the next one does. The network extends through the entire piece of glass, connected and continuous, but bent and twisted in ways that never repeat. This is why glass is transparent, while quartz, in its crystalline form, is often white or cloudy. When light passes through a crystalline material, it encounters the regular boundaries between crystal grains and is scattered in multiple directions, producing opacity. In glass, there are no such boundaries. The network is continuous and disordered, and so light passes through largely unimpeded. The disorder, paradoxically, is what lets you see through it. Now, pure silica glass. Glass made from nothing but silicon dioxide melts at around 2,300 degrees Celsius. This is an almost impossibly high temperature for most practical purposes. Ancient furnaces could not reach it. Even modern industrial furnaces find it inconvenient. So glassmakers, for thousands of years, have added other materials to bring that temperature down. The most important of these is soda ash, which is sodium carbonate. When sodium carbonate is added to the silica melt, the sodium ions, sodium atoms that have given up one of their electrons and carry a positive charge, nestle into the glass network and break some of the silicon oxygen bonds. These broken bonds are called non-bridging oxygens because they are bonded to only one silicon atom instead of bridging between two. The presence of non-bridging oxygens makes the network less rigid, less tightly connected, and the whole thing becomes fluid at a much lower temperature, around 1,500 degrees Celsius with a typical soda addition. This is still very hot, but it is achievable. Ancient furnaces could reach it with sufficient fuel and good design. The problem with adding sodium is that it makes the glass soluble. A glass made of just silica and soda ash would slowly dissolve in water, not useful for a bottle or a window. So a third ingredient is added, limestone, which is calcium carbonate. The calcium ions that enter the network from limestone restore some of the structural integrity that the sodium ions removed. They fill the gaps, bridge some of the non-bridging oxygens, and produce a glass that is durable, stable, and water-resistant. This three-ingredient combination, silica, soda ash, limestone, is soda-lime glass, and it makes up the vast majority of the glass in the world today. The windows in your room, the bottles in your kitchen, the windscreen of every car on the road, all of it is, at its core, this same ancient recipe. There is one more thing worth exploring here, and it is perhaps the most fascinating and still debated aspect of glass science, the glass transition. This is the boundary, during cooling, where a liquid stops flowing and becomes a rigid solid, but without ever forming a crystal. In ordinary materials, when a liquid cools to its freezing point, it crystallizes. The atoms lock into their ordered arrangement, and the transition is sharp, above the freezing point, liquid, below it, solid. Glass does not do this. As a glass-forming melt cools, its viscosity increases continuously. It becomes thicker, slower, more reluctant to flow, but there is no sharp moment of crystallization. Instead, at a temperature called the glass transition temperature, the viscosity becomes so high that the material behaves, for all practical purposes, like a solid. It no longer flows on any timescale relevant to human experience, but its atoms are still in their disordered, liquid-like arrangement. It is a solid that remembers being a liquid. The exact molecular mechanism of the glass transition is something that physicists and materials scientists have been working on for decades, and it is not fully resolved. What happens at the atomic scale as the viscosity climbs through those final orders of magnitude? Why do some materials form glass easily while others always crystallize? The broad answers are known, but the fine details are still being worked out. And this is a good place to address a persistent and charming myth. You may have heard that the glass in old cathedral windows is thicker at the bottom than at the top because glass slowly flows downward over centuries like a very slow liquid. It is a lovely idea, and it is not true. Glass at room temperature does not flow on any human timescale. The viscosity is far too high, by many orders of magnitude, for any movement to occur in thousands of years, let alone centuries. The reason old window glass is thicker at the bottom is much simpler and rather more interesting. It was made that way. Ancient methods of producing flat glass, particularly the crown glass method, in which a gather was spun into a flat disc by centrifugal force, produced sheets of uneven thickness. When glaziers installed these panes, they placed the heavier edge at the bottom, both for stability and because it was common sense. The glass is thicker at the bottom because it was installed that way, not because it moved. What glass actually is, then, is this: a continuous, disordered network of atoms, frozen in the configuration they happen to occupy when the cooling outran the crystallization. A solid that carries the memory of being a liquid, patient, still, holding its shape, not because it has settled into an ordered arrangement, but because it has simply stopped mid-flow and never started again. There is a furnace in a glass factory, one of the large flat glass factories that produce the windows of the world, that has been burning continuously for somewhere between 8 and 12 years. It will not be switched off until it is worn out and needs to be rebuilt. These furnaces run day and night, 7 days a week, year after year, because the cost of stopping them and restarting them is enormous. The glass inside them is never allowed to cool. It simply flows from one end of the furnace to the other in a slow, continuous river of molten light. At one end of the furnace, raw materials are fed in: sand, silica, sand, chosen for its purity, with an iron content carefully controlled because even traces of iron affect the color of the finished glass. Soda ash, limestone, small amounts of magnesium oxide and aluminium oxide added to improve durability, and cullet, broken recycled glass, added to the batch because it melts more readily than raw materials and reduces the energy required. A modern glass furnace might use 20 to 30% cullet in its batch. The furnace takes all of this and, over the course of many hours, transforms it. The temperature inside the melting end of the furnace reaches around 1500 degrees Celsius. At this temperature, the raw materials react and dissolve into each other, the gases driven off, the melt homogenizing into a viscous, glowing liquid. Then it flows forward through the furnace, cooling slightly as it goes, until it reaches the working end at a temperature suited for shaping. And here is where one of the most quietly extraordinary inventions of the 20th century takes over. In 1959, a British engineer named Alistair Pilkington, working for the glass company that bore his family's name, announced a new process for making flat glass. He called it the float glass process, and it was built on an idea so elegant it seems obvious in retrospect, though it had taken years of development and a great deal of failed experimentation to reach. The idea was this: if you pour molten glass onto a bath of molten tin, the glass will float. Tin is denser than glass, so the glass sits on top of it without sinking. And because both the glass and the tin surfaces are liquid, the interface between them is perfectly flat. The glass spreads out across the tin bath under the influence of gravity, reaching an equilibrium thickness of around 6 or 7 millimeters on its own. Thinner sheets require the glass to be stretched, thicker sheets require it to be held back. And because both surfaces are in contact with perfectly flat liquid surfaces, both faces of the glass emerge smooth and parallel, without the grinding and polishing that flat glass previously required. The tin bath is enclosed in a carefully controlled atmosphere of nitrogen and hydrogen to prevent the tin from oxidizing. The glass enters the bath hot and fluid at one end, floats forward slowly, cooling as it goes and exits at the far end as a solid ribbon, still warm but no longer able to flow. It moves forward at a steady pace, and robotic cutters score and break it into sheets of the required size, which are then stacked and shipped. Around 90% of all the flat glass in the world, every window in every building, every car windscreen, every glass door, is made by this process. A river of glass floating on a river of liquid metal, perfectly still and perfectly flat. The story of glass bottles and containers is different, and it has its own remarkable chapter. For most of history, glass containers were made by hand, by glassblowers, one at a time, each bottle a small individual act of craft. The production rate was limited by the speed of human hands and lungs. Then, in 1907, an American inventor named Michael Owens patented the first fully automated bottle-making machine. Owens had spent years working in glass factories, and he understood the process intimately. His machine replaced the glassblower's breath with a mechanical suction that gathered molten glass from a feeder, formed it into a parison, a rough cylindrical blank, and then blew it into a mold to produce the final shape. The machine had multiple arms, each going through the sequence simultaneously, and it could produce around 2,500 bottles per hour. This was a transformation so complete that it reshaped the economics of the entire glass industry. The machine ran on, indifferent and tireless, doing in an hour what a team of skilled glassblowers might take days to accomplish. But whether glass is made by floating on tin or being blown into a mold, it faces the same challenge when it leaves its forming process: internal stress. When glass cools unevenly, when the outside cools faster than the inside, or when different parts of the piece cool at different rates, the outer layers contract and try to pull inward while the inner layers are still hot and expanded. The outer layers are in tension, the inner layers in compression, and the result is a piece of glass that is significantly weaker than it should be, prone to cracking along these internal fault lines. Sometimes, if the stress is severe enough, a piece of glass will crack spontaneously for no apparent reason, simply because the forces locked inside it have found a path to release. The solution is annealing, a word that comes from the Old English for heat, and which describes the process of slowly and carefully reheating glass to a temperature just below the glass transition, holding it there long enough for the atoms in the network to relax slightly, and then cooling it down again at a controlled, very gradual rate. In an annealing layer, a long, tunnel-like oven through which glass moves on a conveyor belt, the temperature drops by perhaps 2 or 3 degrees per minute through the critical range. This gives the glass network time to equilibrate, to release the stresses that rapid cooling had locked in. The result is glass that is far stronger and more stable. Annealing is not optional. Every piece of glass you have ever used has been through it. There is something quietly satisfying about the image of that float glass ribbon, emerging from the furnace, spreading itself across the still surface of the liquid tin in the cool dark of the bath chamber, finding its own perfect flatness by the most patient of physical laws. No grinding, no polishing, no human hand required. Just gravity, and the willingness of a liquid to find its own level. There is a type of glass that, when you hold it up to a candle, does not merely transmit the light. It catches it, bends it, splits it into its component colors, and throws small rainbows across the walls of the room. It is heavier than ordinary glass, with a satisfying weight in the hand. When you tap it gently with a fingernail, it rings, a clear, sustained note that fades slowly, like a distant bell. This is lead crystal, and its invention in London in 1674 belongs to a man named George Ravenscroft. Ravenscroft was an English merchant who had spent time in Venice, then the glass-making capital of Europe, and returned to England determined to produce a high-quality glass that could compete with the famous Venetian product. Ravenscroft experimented for years, and the key discovery he made was the addition of lead oxide to the glass batch. Lead is a heavy element, and the lead ions that enter the glass network are larger than the sodium and calcium ions in ordinary soda-lime glass. Their presence in the network increases what is called the refractive index of the glass, which is a measure of how much the glass bends light as it passes through. A higher refractive index means the glass bends light more steeply, and when light is bent steeply enough, it separates into its constituent wavelengths, its colors, producing the prismatic sparkle that makes lead crystal so distinctive. Ravenscroft patented his formula in 1676, and within a generation, English lead crystal had become one of the most sought-after luxury materials in Europe. The cost of that beauty, we now know, was not negligible. Lead is toxic, and the lead that leaches from crystal glass into acidic liquids, wine, fruit juice, spirits, over long periods of storage can reach levels that are not trivial. Modern lead crystal decanters are generally considered safe for serving, but not for storing wine for months. The beauty and the hazard were always inseparable, though for 3 centuries no one knew to look for the hazard. George Ravenscroft worked by intuition and experience in the tradition of craft knowledge that had shaped glassmaking since Mesopotamia. He understood what worked, even if he could not have explained why in chemical terms. Otto Schott was a German chemist who, in the 1880s, began approaching glassmaking as a branch of chemistry rather than a guild tradition. He was trained as a scientist, not as a glassworker, and he brought to the problem a systematic rigor that the field had never seen before. Working initially from his home, and later in collaboration with the physicist Ernst Abbe and the optical instrument maker Carl Zeiss in the city of Jena, Schott began methodically testing the effect of adding different elements to glass. He worked his way through the periodic table, measuring how each addition changed the optical properties, the thermal properties, the mechanical properties of the resulting glass. He kept detailed records. He published his findings. The glasses that emerged from Schott's laboratory were not like anything that had existed before. By adding boron to the glass network, he produced a glass with a much lower thermal expansion, meaning it expanded and contracted much less when heated and cooled than ordinary soda-lime glass. This borosilicate glass could withstand rapid temperature changes without cracking, which made it ideal for laboratory equipment, for telescope lenses, and eventually, in the hands of other researchers at Corning Glass Works in America, for the oven-proof cookware that became Pyrex. Schott's systematic approach laid the foundation for modern glass science, and for the idea that glass composition could be engineered rather than discovered by accident. But perhaps the most extraordinary accident in the history of glass science happened not in Schott's laboratory in Jena, but in a laboratory at Corning Incorporated in New York State in 1953. The scientist involved was S. Donald Stuckey, and the accident involved a furnace that went wrong. Stuckey had been working on photosensitive glass containing tiny amounts of gold or silver compounds that, when exposed to ultraviolet light and then heated, would cause microscopic metal particles to precipitate out of the glass network, forming a latent image, somewhat like a photographic film. It was interesting work, with potential applications in data storage and decorative art. One day, he placed a sample of photosensitive glass in a furnace and set the temperature to about 600 degrees Celsius. Something went wrong with the furnace controls, and the temperature climbed to around 900 degrees without his knowing. When Stuckey opened the furnace, he expected to find a puddle of melted glass. Instead, he found a white, opaque, ceramic-looking material. The sample had not melted, it had transformed. What had happened, he quickly understood, was that the tiny metal particles that had precipitated out of the glass during the earlier processing had acted as nucleation sites, seeds around which crystals could begin to grow. At the higher temperature, crystals had grown throughout the glass, transforming it from a disordered amorphous solid into a material that was partly crystalline. But unlike most crystalline materials, which are brittle and prone to cracking along crystal boundaries, this glass ceramic, as Stuckey named the new class of material, was extraordinarily tough. When he dropped the sample, accidentally, it bounced. It did not shatter. The material Stuckey had discovered, which was later developed under the trade name pyroceram, had properties that no pure glass and no pure ceramic could match. It was transparent to radar. It could withstand enormous temperature changes without cracking, far better even than borosilicate glass. It was used for the nose cones of guided missiles, where the material must survive both the cold of high altitude and the heat of atmospheric friction. It became the basis for Corningware, the white ceramic cookware that could go directly from a freezer to a hot oven without cracking. And the same principle, using controlled crystallization within a glass matrix to produce new properties, was later applied to photochromic lenses, the eyeglass lenses that darken in sunlight and clear again indoors. Photochromic lenses work because they contain tiny silver halide crystals, silver atoms bonded to halogen atoms in the same family of compounds used in photographic film, dispersed through the glass. When ultraviolet light from the sun strikes the lens, it causes a chemical reaction that releases silver atoms which cluster together into tiny metallic particles that absorb visible light, darkening the lens. When the ultraviolet light is removed, the reaction reverses. The silver atoms reabsorb halogen atoms and return to their transparent form. The cycle can be repeated thousands of times. Stuckey's accidental furnace had opened a door to a whole new way of thinking about what glass could be. What connects Ravenscroft, Schott and Stuckey is not just that they each changed glass. It is the way they changed it. Ravenscroft worked by feel and intuition, guided by the craft traditions of his time, and stumbled onto something beautiful. Schott worked by systematic science, mapping the entire space of possible glass compositions with methodical patience. Stuckey worked by intention and was redirected by accident, by a furnace that didn't behave, by a sample that refused to melt, by the willingness to look at an unexpected result and ask what it was rather than discarding it as a failure. 3 different ways of knowing. 3 different ways of knowing. Somewhere beneath the Atlantic Ocean, resting on the seafloor in the cold and the dark, there is a cable. It is not much to look at. Roughly the diameter of a garden hose, armored with steel wire and waterproof sheathing. But inside that sheathing, at the cable's core, are strands of glass. Each strand is thinner than a human hair. And through each strand, right now, light is traveling, carrying emails, telephone calls, financial transactions, video streams, the accumulated traffic of the internet, at roughly 2/3 the speed of light in a vacuum. These strands are optical fibers, and they are among the most remarkable objects that human beings have ever made. The glass in an optical fiber is not ordinary glass. It is made from ultra-pure silica, silicon dioxide, with an impurity level so low that it is measured in parts per billion. To understand what that means, ordinary window glass contains iron and other trace elements at the level of parts per million. Optical fiber glass is 1,000 times purer. If the glass in an optical fiber were as impure as ordinary window glass, light would be absorbed within a few meters and the signal would die. With the extraordinary purity of fiberglass, light can travel through kilometers of it and still emerge with enough strength to be detected. The principle that makes this possible is called total internal reflection. When light travels through a denser medium, glass for instance, and encounters a boundary with a less dense medium, air, or a different type of glass, it is refracted, bent as it crosses the boundary. But if the angle at which it hits the boundary is shallow enough, if it is traveling nearly parallel to the boundary rather than nearly perpendicular to it, something different happens. Instead of passing through, the light bounces back entirely. Every photon is reflected, none escape. This is total internal reflection, and it is the reason a fiber optic cable works. The fiber is constructed with a central core of very pure, high refractive index glass surrounded by a cladding layer of slightly different glass with a lower refractive index. Light entering the core at the right angle bounces between the core cladding boundary as it travels along the fiber, never escaping into the cladding, guided from one end to the other as if the glass were a pipe for light. The development of practical optical fibers happened gradually through the 1960s and 1970s, driven in large part by work at Corning Glass Works, where researchers Charles K., who later received the Nobel Prize in Physics for his foundational work on the theory of optical communications. The first transatlantic fiber optic cable was laid in 1988, and since then the network has grown to encompass hundreds of thousands of kilometers of undersea cable connecting every continent except Antarctica. The Internet, in its physical form, is largely a network of glass threads on the ocean floor. Glass has also found a very different kind of application in the screens of the devices you carry. The glass in a modern smartphone screen is chemically strengthened glass, and the process that strengthens it is worth understanding because it is genuinely elegant. Ordinary glass, when it cracks, does so because a small surface flaw, a scratch, a tiny chip, concentrates stress at its tip. As the stress at the tip exceeds the strength of the glass network, the crack propagates. The way to prevent this is to put the surface of the glass into a state of compression, to squeeze it, so that any crack trying to propagate must first overcome that compressive force before it can open and spread. The technique used in the glass known commercially as Gorilla Glass and developed by Corning involves immersing the glass in a bath of molten potassium salt at around 400 degrees Celsius. The glass contains sodium ions in its network. At this temperature, potassium ions from the salt bath migrate into the glass surface, swapping places with the smaller sodium ions that are already there. Potassium ions are larger than sodium ions. They take up more space in the network. As they force their way in, they push the surrounding glass structure outward, creating a state of compression in the surface layer. This compressed surface is significantly harder to crack. The glass is not stronger in an absolute sense. The network is the same, but the compressive stress means that any crack must work against that compression before it can grow, and for typical impacts and scratches, it never can. The result is the glass that survives being dropped on pavements, bounced in pockets, pressed with keys and coins in a way that ordinary glass never could. The most unexpected territory that glass has entered, though, may be the human body itself. In the late 1960s, a materials scientist named Larry Hench at the University of Florida was working on the problem of biocompatibility, the challenge of making artificial materials that the body would accept rather than reject. Most implant materials at the time were chosen for their inertness: titanium, certain plastics, aluminium oxide ceramics. The body would tolerate them because they did not react with the surrounding tissue. Hench had a different idea. He wondered whether a material could be made that the body would not merely tolerate, but actively bond with. A material that would react with living tissue in a controlled way and become integrated with it. What he developed was a glass containing silicon dioxide, calcium oxide, sodium oxide, and phosphorus pentoxide in specific proportions. When this glass is implanted next to bone, it undergoes a series of surface reactions. Ions dissolve out of the glass surface into the surrounding fluid. A layer of calcium phosphate, the same mineral that makes up the mineral component of bone, forms on the glass surface. The body's own bone-forming cells, called osteoblasts, recognize this surface as similar to their natural environment and begin to grow onto it, bonding the glass to the living bone. It is used today in dental surgery, in the repair of bone defects, and in the treatment of certain types of bone cancer, where glass granules are packed into the cavity left after tumor removal and the surrounding bone grows into and around them. There is research ongoing into glass that can go further still. Glass scaffolds that dissolve slowly inside the body as new bone grows in to replace them, disappearing as they are no longer needed. and glass particles engineered to carry chemotherapy drugs, delivering them slowly to a tumor site from within the glass network, releasing their payload as the glass surface gradually reacts with the surrounding fluid. The same disordered atomic network that first formed in a volcanic eruption, that was shaped by Stone Age hands into an arrowhead, that a Phoenician artisan inflated with a single breath. It is pressed into the surface of the device in your pocket, compressed and hardened against the small violences of daily life. It is, in some people, woven into the fabric of their bones. There is a beach somewhere. There are many beaches, really, on every coast of every continent, where the sand underfoot is mostly silica. It arrived there over millions of years. Rock eroded by rain and wind and the slow persistence of rivers, ground finer and finer until it became grains small enough to be carried by water, deposited at the margin where the land meets the sea. Each grain is a tiny piece of the deep past. The silicon in it was forged in the interior of a star that died before our sun was born, scattered into space, gathered into the dust cloud that became our solar system, incorporated into the rock of the early Earth, carried through geological ages of heat and pressure and erosion to arrive, finally, here. Under your feet. Waiting. Under your feet. Waiting. It is a long journey for something that ends up as a window. We have followed glass tonight, from its volcanic origins to the ocean floor, from the first obsidian blade to the chemically strengthened screen, from a clay tablet recipe in Nineveh to a furnace in New York that accidentally invented a new class of material. Glass has been, in turns, a luxury of pharaohs, a common household object, a carrier of light, a scaffold for living bone. It has been shaped by breath and by gravity, by the systematic patience of scientists, and by the happy inattention of a furnace controller who set the wrong temperature. And yet through all of that, the essential nature of glass has not changed. It is still, at its heart, what it always was, a disordered network of silicon and oxygen atoms, frozen mid-motion, caught between the liquid it was and the crystal it never became. The glass in a Roman wine cup and the glass in a transatlantic cable share the same fundamental atomic structure, the same frozen chaos, the same patient stillness. The questions that remain open in glass science are, in a way, appropriate to the material. Glass has always resisted easy explanation. The glass transition, that boundary where a cooling liquid stops flowing and becomes a rigid solid without crystallizing, is still not fully understood at the molecular level. Scientists can measure it precisely. They can tell you the exact temperature at which a given glass composition transitions. They can describe the dramatic increase in viscosity that accompanies it, rising over many orders of magnitude in a narrow temperature range. But the precise molecular mechanisms, why the viscosity climbs so steeply, what is happening at the atomic scale in those final degrees of cooling, remain an active area of research, debated in the pages of physics and materials, science journals. It is one of the more quietly humbling facts of modern science. A material that humanity has been making for 5,000 years still holds, at its most fundamental level, a question that has not been fully answered. There is also the question of energy. Making glass is expensive in terms of heat. The furnaces that melt sand run at 1500 degrees Celsius, consuming enormous quantities of fuel, producing significant carbon dioxide. The glass industry has been working for years on reducing this cost, improving insulation, increasing the proportion of recycled cullet, optimizing furnace design. But the most promising avenue is the search for genuinely lower temperature melting, perhaps through new flux combinations, perhaps through entirely different synthesis routes that bypass the need for a high temperature melt altogether. Some researchers are investigating whether glass-like materials can be produced from waste streams, volcanic ash, rice husks, certain industrial byproducts that require less energy to process than conventional raw materials. the ancient recipe is being quietly rethought. And then there is self-healing glass. It sounds like something from a much further future than it actually is. Certain experimental glasses developed in research laboratories over the past decade have been shown to repair microscopic cracks under specific conditions, elevated temperature, or the presence of moisture, or simply time. The mechanism involves the slow diffusion of atoms in the glass network, filling the void left by a crack in the way that very thick honey might slowly close around a gap. The healing is not fast, and it does not work for large fractures. But for the microscopic surface flaws that initiate cracking in the first place, there is genuine evidence that carefully designed glass compositions can, given enough time and the right conditions, close them. The material that has always seemed the very definition of irreversible breakage may, in its most carefully engineered forms, be learning to repair itself. Glass holds time in a way that few other materials do. The sand that became it was shaped over hundreds of millions of years. The recipe for melting it is 5,000 years old. The glass in a medieval cathedral window has been standing in the same stone frame for 7 or 8 centuries, holding the same light, and it will likely still be standing long after everything else in the building has been replaced. Glass does not rot. It does not corrode in ordinary conditions. It does not burn. If it survives the initial risk of breakage, it is among the most durable materials that human beings have ever worked with. A piece of Roman glass, 2,000 years old, can still be held up to the light and seen through. The transparency is still there, a little dimmed by a thin layer of surface weathering, but still present. Still doing what it was always made to do. There is a particular quality to light seen through glass that is difficult to describe, but immediately recognizable. The way a window holds the world on one side and the room on the other simultaneously. The way early morning light comes through a pane of glass and lands on the floor in a shape that is almost but not quite the shape of the window, softened at the edges, carrying something of the outside into the inside. Glass is, in a sense, a threshold, a material that divides without separating, that lets you see without touching, that holds two worlds in contact without merging them. The sand underfoot on that beach, the furnace burning through the night, the breath of an unknown artisan on the Syro-Judean coast 2,000 years ago inflating a gather of molten glass into a bubble of light, the float bath, still and silver, with a ribbon of glass moving slowly across its surface. A strand thinner than a hair, carrying the internet beneath the ocean, a piece of glass bonded to living bone, becoming part of a body. All of it the same material, all of it the same frozen moment, the same atoms caught mid-tumble, the same patient refusal to become a crystal. The window beside you has been holding the dark outside and the quiet inside for as long as you've been in this room tonight. It will still be holding them long after you're asleep. You don't need to do anything with that. It's just a small and gentle thing to notice before you drift. Whatever you were carrying when you lay down tonight, whatever the day left behind, you don't need it now. It can wait on the other side of the glass with everything else that belongs to the waking world. The sand has had its millions of years. The furnace has had its long burning night. The glass has found its stillness. And so, now, can you sleep well?